very likely Monday. I don't know. I haven't actually checked my email.
Yeah.
Already yet?
Oh, yeah, yeah.
Right. Yeah. So probably cancel some Monday. Stay safe, everyone. Back up. Okay, so just to remind you, if you go to this link, myname.com/teaching, the first link will be the link to the course. And there you'll find the version of the book that we're using. I'm continuously updating it, but not updating the exercise numbers anymore to get them correct. No. So the exercises are fine now, right? Okay. So yeah, it'd be good to start working on them. And we'll have office hours every Monday, 4 to 5 p.m. Okay. And anyone's welcome to come to that, even though it's not registered for whatever questions. We can even talk about life, you know, whatever. So, okay. I think if there's anything else of the administrative nature. All right. Good. So last time we were talking about the repetition code, and I'll just review that very briefly. So we talked about a binary symmetric channel. The bit gets through with probability 1 minus p, or it flips with probability p. Okay. And then we said, you know, if you do a simple repetition code, this is rate 1/3. So 1 information bit per 3 physical bits sent over the channel. And the error probability, the decoding error probability goes from p to order p squared. Right? And then we said, oh, you can concatenate, which means you send each physical bit through the same encoding. In this case, it's simple. It's another repetition code. And we argue that the rate, you know, I mean, it's obvious it goes to 1/9, and then the error probability goes to e to the 4th. And you can keep doing this. And the problem with this scheme is that the rate tends to 0. You know, not only does it's good that the error probability tends to 0, but then the rates tend to 0. So it's like a useless coding scheme in practice. Okay, so the question is there something better we can do? Yes, there is. This is what Shannon discovered. So now we're going to talk about Shannon's channel coding theorem. Okay, now we imagine that there's a noisy classical channel described by a conditional probability distribution. And this can generalize the binary symmetric channel. Okay, so this is a pretty general form of a classical channel. We are considering a finite alphabet for both input and output. You can modify this assumption to have a continuous alphabet, like if you have it's called Gaussian channel. But we're not going to look at that. But many of the ideas conceptually are the same. Okay? So what are we interested in? We're interested in, we want to know its capacity. Okay? And this is a keyword. What is the channel capacity? So it's something that's operationally defined, okay? It's an optimization problem. So it's also defined in an asymptotic way. Okay, so right now we're just going to state it in kind of an informal way. the capacity of the channel, py given x, is equal to the maximum number of bits per channel use that we can transmit that the sender. So the sender has access to all the inputs to the channel, and the receiver has access to all the outputs. So the maximum number of bits per channel use can transmit such that the error probability tends to zero as the number of channel use goes. This is the number of channels. Right? So it's an asymptotically defined quantity, just like the data compression limit is defined in an asymptotic limit. We were pretty informal with that also. This is the main idea behind the, this is how you define. We're also making an assumption. The channel is called in an IID way. Again, that's the keyword, independent and identically distributed. So, what does that mean? Let's just write it formally. So, this will be the channel probability distribution. We will call it channel law, or n channel use. What we're assuming is that this fact, and again, we're using this information theory shorthand, where a big Yn means a sequence of random variables, y1 through yn, and the same for the big Xn. And these are the actual realizations of the random variables. Y to the n is a sequence, little y1 through little yn. So this is the assumption that we're making, the IID assumption. So every channel use is the same, and it factors. It's nice to have a picture in mind, and this is the common kind of picture we'll draw. This is a random variable m corresponding to the message to the sender. We usually call the sender Alice. There's an encoding for the n channel usage. And then I'm also going to use this shorthand. Big N is the same as the shorthand for the noise channel. Okay? So the channel big N is being called little n times. And then, the receiver, Bob, makes an estimate, m hat, of the message that was transmitted. What is the error probability? The error probability is this. Okay. Right. And then technically you could think of, if you want the scheme to work for every possible message that you can send, you can take a maximum over all probability distribution you have on the message. And due to convexity, or the way this expression will appear mathematically, this is equivalent to the maximum of the error probability condition on sending particular messages. Right? Like this will be the same as max with the M. And message set. Now I'm using this kind of curly M for the message set. All right. We can also allow for, yeah. Probability distribution of the messages. Okay. And if we want to get a little more technical, we can define what we call an N M epsilon code. Okay. What does this mean? It's just these are the three parameters that are the relevant performance parameters of the protocol for a fixed number of channels. The little n is the number of channels. Okay. This is the size of the message set. That's how many messages you can transmit. We'll say it's an NM epsilon code if this error probability is less than epsilon. So epsilon will be a number between 0 and 1. Right? And the rate of the code is the number of bits, right? So if there are 8 messages, you can encode 8 messages with 3 bits, right? So the binary logarithm of the number of messages is the number of bits that you can transmit. The rate is log base 2 divided by the number of channels. So those are the various terminologies that we have. And yeah, so in a rough way, the capacity is such that it's the max. You think of the rate being like a constant rate that you're trying to hit. Okay. So it's the maximum rate you can achieve such that there exists a sequence of these NM epsilon codes where in the sequence, the rate is converging to a constant. Okay. This log m over n is converging to a constant. You should, another way to write this is it's called here. This is the rate. We want to maintain a constant rate. If you rewrite this formula, the size of the message set has to be growing exponentially with the number of channels. You want to maintain a constant rate for the sequence of code. Okay? So that's how you should be thinking. The rate is convergence towards a constant, while the error probability is tending to 0. Okay? And so if there's a rate if there's a sequence of codes with this property, that rate is called achievable rate. And the largest achievable rate is the capacity. Okay, so that's how we think about it. That's how Shannon thought about it. Why is that interesting? Well, in actual communication team, this is what you want. You want to have a very large rate of communication, and you don't want there to be error. You want to understand what you're doing. All right, so it's operationally relevant. Okay. Any questions about this stuff? This is like the basic block diagram. One thing I'll say is that in this definition, you don't have to, but you can allow the encoding to be stochastic probabilistic. You can also allow the decoding to be probabilistic. Right? Turns out that doesn't help for this task, but for other tasks, it can help. Like if you want this message to be private from the eavesdropper, suppose the channel had another output port and went to an eavesdropper, then it turns out that stochastic encoding can help. You have to make use of it. Right? Then when we go to quantum, we can do all kinds of variations, right? So outcome eventually, the message that we're sending can be classical or quantum, right? Get to that eventually. If the message is classical, the channel's quantum, the channel would accept the quantum input, and then your encoding would be translation from a classical message to a quantum input. And if you're familiar, a lot of you are familiar with quantum optics, you could encode a message into coherent states. And for many channels of interest, that's actually optimal. Okay, that'll come later. When we go to quantum, the outputs of the channel can be quantum. And what you do instead of what generalizes the decoding is a measurement. Okay, we'll get to the theory of quantum measurements eventually. And measurement can be doing individual measurement for each channel output. That would correspond to what's traditionally done in communication schemes. But in the quantum world, you can perform what's called the collective method. You can allow for a general quantum computation and then do individual measurement, figure out what the message was. And it turns out that can improve rates of communication. Okay? So then we could also allow the message to be quantum. And then it's like we're trying to shuffle qubits around from one location to another. Right? We want to do distributed quantum computing. Okay. All right, but for now, let's think about what Shannon did. And to think about that, we'll start again with the kind of simple example. And you're going to look at it and eventually I think you'll agree it's quite simple, but then conceptually, it turns out to be nearly like the general. Okay. And we had that kind of thing with data compression, right? We looked at a very simple example with just like 8 symbols, and there was like a high probability set and low probability set. But then that ended up being essentially conceptually the same as the general case of typical sequence. All right, so we'll do something similar. Okay, so and again, all we're going to talk about, just like we did for compression, we're just going to talk about the coding scheme. We're not going to talk about why it's optimal. Right? That kind of thing will come later. So this is an idea. There's a famous book on classical information theory by Cover and Thomas. Cover, the name looks like cover, and Thomas is the other person. So that's a very nice book on classical information theory if you want to delve into that more. They talk about a noisy typewriter. So what does it do? It's meant to be like someone who's making mistakes. Maybe the typewriter itself makes mistakes, but like you're intending to hit one key and you accidentally hit a nearby one. All right, so it looks like this. This is like the transition probabilities. So there's going to be 4 input symbols, A, B, C, D. And if you hit A, or if you intend to send the message A actually comes out with probability 1/3. And then You can instead accidentally go to E, or you can go to B. And then similar kind of thing for B, you transition to the correct thing with probability 1/3. It's all 1/3. Okay, so let's think about the channel for a minute. When can we have error? Suppose that we decide to use all the symbols at the input, then we can have problems in decoding, right? It's like, if I'm the receiver and I know that the sender's using all the symbols, if I decode B, it's unclear what the input was, right? Because it could have come from here or it could have come from here. Right? So if we use all symbols, input, and then we cannot decode space. Right? The general case, what does it mean? What does this correspond to in the general case? We have a P of Y given X, right? And it's like we're using all the symbols to code information. And so what you're doing there potentially is exceeding the capacity of the channel, right? And we haven't said this yet, but your intuition should be is that if the rate at which you're coding exceeds the capacities, then you cannot make this happen. You cannot make the error probability grow. Then goes to infinity. It's like you're overloading the channel, and you're actually doing something that's physically impossible. Okay. And for the IID case, that would be like if your message set, this corresponds to in the message set be the set of all symbols, right? Input alphabet, Cartesian products, and fold Cartesian products. If you have a noiseless channel, then you can do this without a problem, right? Like for the binary symmetric channel, if P was 0, then indeed you could send 1 bit per channel and you'll be fine. But otherwise, it's like you're overloading. Okay. What can we do instead? You could make
have non-overlap like A and C.
Perfect. Yeah. So you can choose a subset. The story is choosing a code, right? So he's saying, all right, all I'm going to do is try to send a bit. The message will be 0 or 1, and the code will be the 0 will map to A, and 1 will map to C, right? And that's an example of a choice of a code communication. And if we want to speak in this language, NM epsilon code, it would be, we're using the channel, N would be 1, we're using the channel once, right? The size of the message set is 2, the error probability is 0, right? Why does this work? Well, you want to send the message 0 and you send A, then A maps to these ones. These ones. This was a brand new mark. And C will map to this. Right? And so then the only possibility is that the receiver will receive one of these 3 or one of these. And then there's a unique mapping. There's a unique input that leads to this out. So you can decode uniquely. And this is actually called a zero error code, okay? Because there's no error probability. Good. And you said another possibility was to use just B or D, right? And then that would be fine. But if you use adjacent ones like A and B, that's when you run into trouble. Okay.
If you are asking, you are changing the basis problem, you will solve initially, right? Because you will send A, B, C, and D, and now you are saying, I cannot.
Yeah. Right. So you have to pick a subset. I mean, initially, I didn't say anything about the size of the method. I said we're given a channel, and then we have to make do with that, and then figure out coding sequence of code and the process. Right? So this is the channel that's given. I didn't say this has to be the message set. I said, well, I don't know if I said anything, but what we can do is choose a subset of the set of all inputs. So what we want to do is, the lesson is that, well, choose M, the message set, to be some subset of the set of all. Sorry. We'll choose a code. Okay, so the C is for a code. And then what the encoding does is it'll map us from the message set to the code words. Okay. So here for this example, 0, 1 is the code. And sorry, that's the message. And the code is okay. Yeah. This was just to give some sense of like the idea behind the coding theorem. So I don't know if I understood your question. Can you say it again?
I'm a little caught up on the premise of why we set up this channel and the alphabet we chose the input.
This particular one?
Well, that in the I get why we would restrict our code. I guess it's kind of related to like the Google's question, where it's like I understand if we restrict our code, we can get zero error by making this unique mapping.
Yeah.
But in reality, how do we use that restricted code to potentially decode the whole message?
Yeah. So in reality, we don't need a zero error code. We just want this error probability to be very small.
Okay. But is it possible that this scenario to get low enough error that it's acceptable, I guess?
For this particular channel, we could do a calculation of a function called mutual information of the channel and figure out what its capacity is. It might be slightly larger than 1 bit per channel use. I'm not sure. I would have to do that calculation. But at the very least, this is achievable, right? We would have to otherwise compute its capacity.
I think I know what you're doing. You're saying if you're not allowed to send B and D, would that be okay? Would we be missing or something? But ABC is not what we want to send. What we want to send is 0 and 1. The message sent.
Well, we want to send as many messages as possible, such that the error probability is small. Okay. So like, if we're using all of them, then we're going to have like, you can calculate what the error probability will be, but it'll be significant, like significantly larger than 1 in a trillion.
So it's what you're really saying is just like if we were to use this channel,
you could not use all the inputs.
This many numbers or this many symbols in the alphabet. You have to restrict our alphabet to reduce the possible message.
Yeah. Right. Yeah. And that's going to be the kind of generic case for noisy channels. You should not use all the inputs because it's like you're trying to cram too much information through the channel. And if you do it, you'll actually, the error probability will tend to 1. That's the number is the Yeah. The number of messages you can send faithfully. That's right. Yeah. There's no reason they can use A, C, or B and A. But if you use A and B, you're going to have a problem. Yeah. Yeah. That's right. Yeah. Good. All right. So now let's talk about more generic. Okay. So for the generic case, or let's say the IID case that we just talked about in our race, there's going to be two main ideas. Conditional typicality. Last time we talked about, Monday and Wednesday we talked about typicality of a sequence. Now we're going to have something called conditional typicality, right? So we have outputs conditioned on a particular input in the transition probability. We have a notion of conditional typicality. And the other big idea is random coding. So if you're a code designer and someone tells you, okay, let's just pick all the symbols in the code words randomly, you might hear this and say, that is a really stupid idea, right? But as Shannon showed, and it's due to this measure concentration factor we talked about, law of large numbers, that actually ends up working well. The sequence is the number of channels you perform. Right? So we'll talk about that and sort of the conceptual aspect. We won't go into detail. All right, let's begin with conditional typicality. So this is for a pair of sequences. And distribution. I want you to think about an input distribution. Correct? And this one's like the channel distribution, right? The conditional probability. So we define the sequence Yn to be delta conditionally typical. With xn. Yeah. And then the next definition is going to look very similar to what we had for typicality, except we're going to use the sample conditional entropy and the conditional entropy. Sample one and the true one. So if this condition holds, this will be the sample conditional entropy. We'll define it in the second. And the true conditional entropy will also be defined. Okay. So this first one is the conditional sample entropy. And it's similar to what we did before. You take the conditional probability that sequence occurred, take its negative logarithm, and normalize. Right? Again, we're assuming this is an IID distribution. So, I mean, a calculation you can do is that using the fact that the log of product is the sum of the log, right? Use that iteratively, and you get this. This one right here is the conditional entropy. And that is defined as an average or expectation of entropy. This is the average over X. And then you take the formula that we had entropy. Apply. So another way to write this is okay, that's another way to write it. So remember before, I'll write it over here. The entropy was defined like this. Expected surprise, right? So now we're kind of adopting this notation. We're saying, well, it's the entropy condition of the value little x. So the random variable big X takes the value of little x. Oops, I made a typo. Conditional probability. So these should all be conditional. Sorry about that. Okay. So that's conditional entropy. And if you want some intuitive way to think about it, you should think that there are two parties. One possesses X, the other possesses Y. And it's the uncertainty that someone who has access to X has about Y. They don't have that. It's like you have some information embodied in the random variable X, and that's your uncertainty about Y. Right? So if you look outside and your side information is that there's no clouds and it's sunny, then you would guess that it's probably not going to rain, right? Or like, you know, if the weather station predicts a hurricane is coming, probably going to happen. So, you know, that's kind of how you think about conditional probabilities, right? And then you just think about uncertainty in some way. Well, I'm saying if you have like knowledge of X, then it produces your uncertainty about Y. And we can make that precise. There's an entropy inequality called conditioning does not increase entropy, or sometimes just beta. So we can write this here. You know, having access to side information produces uncertainty. Okay. Oh. rapidly running out of time. So the conditionally typical set, right like this. It's a function of, there has to be a fixed sequence xn. There's a delta parameter, and it's all the y sequences such that this condition holds. Right? I'll just put a star for this condition, right? And then it's all the y. That's the condition. What do we know about this from the law of large numbers? What did we know about the typical set? If we picked a sequence randomly, it was highly likely that it landed in the typical. Okay. The way you can intuitively think about this is if we pick an xn at random, then it's highly likely that a yn, so if we pick the xn at random and we learn its value, then it's highly likely that if we pick a yn according to this distribution, it'll land in the conditionally typical set. All right, so let's write it down. This is the formal statement. We're using a certain notion of typicality. It's actually called weak typicality. So there's a little thing we have to do with to take an expectation over the x sequence. But this is what we can say. Rigorously. And this is again for all epsilon in 0 to 1, delta greater than 0, and north. That's the statement. There's another notion of typicality called strong typicality. And the statement you get there is that if the sequence xn is strongly typical, then it's highly likely the random sequence yn will be conditionally. All right. Because we're using this notion of weak typicality, we need this expectation. All right. So, but the way you should think about it is that, like, you're given a sequence xn, just think that the sequence xn is typical because it's highly likely anyway. And then once you know what that sequence is, if you pick the yn according to this distribution, the IID1, it's highly likely to land in the condition typical set. All right. This inequality will actually be very important. We'll return to that later. Another thing you can prove about the conditionally typical set, the proof is similar to what we did previously. It's a bound on the size of the conditionally typical set. So the size of this set is no larger than an exponential in the conditional entry, plus the little delta. Okay, we have that bound, and that will be important. All right, and I'd like to, we wrote the formula before, but I want to remind you, the relevant formula will now be mutual information. We wrote that on the board in the first lecture. So the mutual information is the sum of the marginal entropies minus the joint entropy. All right. And you can use definitions to show that h of y minus h of y given x. So you can combine minus joint entropy and plus entropy of X, get this conditional entropy. That's just like a short algebraic calculation with logs, etc. Okay? But writing the mutual information in this way will be how we will think about the capacity theorem. And combined with this one, that conditioning doesn't increase entropy, you can conclude that the mutual information is non-negative. Okay. We didn't prove this, but I believe it amounts to just like concavity of logarithm. Okay. So, all right. That's a joint entropy. So what you do for that one is you use the joint distribution. Rather than plugging in this distribution, you plug in the joint one.
So there's two separate, there's the joint.
That's right. That's right. Yeah. And like the key difference between this one and the joint one is that the argument of the law is the conditional probability. Okay. Let's talk about the next big idea. I would like to finish this off. So I don't know if y'all mind. We'll go like 5 or so minutes past the top. All right. What is random coding? So if you think of, yeah. Oh, thank you. Yeah. Yeah. I mean, this calculation gives you a number, and that number should be larger than that. Sorry about that. Thank you. Okay, so if you think about analyzing the error probability of particular coding schemes, that's a pretty challenging problem. A lot of people have done that in their research since Shannon, but Shannon thought that was too difficult, so he wanted to come up with some clever way to like symmetrize the analysis of the error probability, such that the error probability wouldn't depend on like the particular code word that you chose, but maybe on just like one of them. Okay? And that was this idea of random code. So the idea is literally this. Pick a code at random. Use this distribution. Use some input distribution, right? And what does it mean? Like, you have a set of messages that you'd like to transmit. So for message 1, you pick the first symbol of the first code word randomly, according to this distribution. So this X1 is the first symbol of the first code word for the first message, right? Then for the next symbol, you again pick it according to this distribution. So you're just like, generating these code words at random, generating these symbols. You do it for the whole code sequence. And so this right here is the first code word. Okay. And that's what you'll input to the first use. That's what you input to the end uses of the channel if you want to send the first message. All right. And when this is done, Alice and Bob are allowed to know which code was chosen. And that's part of the game. Okay. So you can almost think of it as like they have shared randomness, right? So like they're allowed to share the outcomes of many coin flips that are used to generate the code words. That's critical that Bob be able to know the actual code that was chosen, right? But the point is that it's chosen randomly, and that's to simplify the error analysis, okay? Message 2, same thing. First symbol chosen at random. Then this makes the second code word. They're all chosen at random. And then the nth message, the code word is also chosen at random. Okay. And then there's this famous saying, like if you allow a bunch of monkeys to like type randomly at a typewriter, then there's a non-negligible chance that at some point they'll like type the words change or discover the coding theorem of Shannon. So you can think of the idea as being like that, like you're over this randomized ensemble of code words that are being selected. There's going to be a non-negligible chance that a good code will be chosen. As long as the message set size is not too large, okay? So what we need to figure out is how large we can make this message set size, right? So this is a key point. The scheme will work. And I'll just give away kind of part of the punchline. As long as the size of the message set is this size. An exponential and the mutual information. That's going to be the key dividing line. As long as, and you have to throw in a little delta, right? Give a little, like slightly less than mutual information. As long as the rate of the code is slightly less than mutual information, the key will work. Remember what we said before, if the message set size is equal to the set of all possible sequences, if the message set is equal to the set of all possible sequences, then it's guaranteed you're going to make an error. If the channel has any noise whatsoever, right? So, but this is the right dividing line. And what you can show is that as long as you choose at this size, there will exist a coding scheme such that the error probability will tend to 0. But if you choose it larger than this, like if you put a plus delta, it's over. The error probability will actually tend to 1.
So that would be like in the first thing we did with like 800.
Yeah.
So that'd be like.
Yes. Yeah. And we're about to draw that kind of picture. And the picture will look precisely like the picture for the noisy type. Correct. So let's do that now, and then that will be kind of the function. Right. So this will be a set of all possible sequences for the input. What are we doing here? We're randomly picking a subset. And let's abbreviate this first sequence to choose the same notation. Superscript n for the sequence. Right? Then here, superscript n. So we've randomly chosen. Okay. Here's the set of all possible outputs. Set of all possible outputs. Okay. we choose the XN sequences at random, Bob doesn't know which, so they're chosen at random, and then Bob's trying to figure out which message was chosen. And so that's also, the particular sequence being sent is not known. Okay. So for a random choice of XN, if we don't know the value, then the distribution from which Yn is selected is this marginal distribution. Okay. P of Y with not conditioned on it. Okay, where the X is like average. Okay. Then if the Yn is selected in this way, according to this distribution, from typicality, it's highly likely that it lands in the unconditioned typical set. Right? That I'm going to draw as some subset, the set of all the typical set. With size, what is the size of this typical set? You can show it's an exponential in the unconditioned entropy. Okay, so this H of Y, which is the first part of the mutual information formula. Okay. So what does Bob know? He knows that he only has to look in this typical set. No matter which sequence was chosen, he knows it's highly likely to land in here. He only has to look there. He doesn't look out, he doesn't have to look outside. Okay? Here's where the non-overlapping set thing comes in. So if you know which sequence was chosen, then according to conditional typicality, the sequence will land in a conditionally typical. I'll draw like this. All right, so that's like what we had with the noisy typewriter, right? Yeah, the picture's gone, but the noisy typewriter, if we were to, since we were using just A and C, there are only like 5 symbols with that map. Right? See? Yeah, but, okay. Let me forget that example, because the reality is that for that example, the set of all output sequences, all output symbols is like the typical set, right? But so we know that if you don't know which one was chosen, it's highly likely it ends up in the typical set. But if you, from the perspective of Alice, who knows which one she's sending, she could figure out, okay, what are the likely output sequences for that symbol, right? This was the definition of conditional typicality, which we had, negative log PYM minus the conditional entropy. So if you knew, if Alice knows the XN that was selected, she can compute the conditions of the set. And we're assuming that Bob also knows the whole code, right? That was an assumption that we made. So he can also figure out these conditionally typical sets. You can calculate what they are. And so for each of these, it looks like this. Right? This one will map to some conditionally typical set, etc. And each of these are the conditionally typical sets, size, roughly 2 to the n conditional entry, right? So that's how you should think about it from an intuitive perspective. We could do all the mathematical proofs, and then this picture would be consistent with the proof. But then it becomes a question of, it's a sphere packing problem, right? It's like, how many of these conditionally typical sets do you cram into the typical set such that they're non-overlapping, right? Because how is Bob going to decode? What is going to be his decoding algorithm? He doesn't know which one is sent. He's just going to ask, oh, is it in this first conditionally typical set? Yes or no? If yes, great, decode as best as one. If not, look at the next one. Is the output equal to that? Do all these calculations. It might take a long time. But in information theory, we don't make any assumption about computational complexity. You know, you just want to understand that comes later. Okay. So, but the decoding algorithm will just be to, you know, the outputs. Bob has the output sequence. You can look at it as a classical thing, right? And then he just does this calculation. Is it in the first one? Is it in the second? Is it in that one? That one, that one? Until he gets a hit. Yes, it's in that one. And then he decodes. And the way the error analysis goes is that, well, if you choose the number of messages to be exponential in the mutual information, that's the number that you can cram in, because the number you can cram in is the size of the unconditionally typical set divided by the size of each conditionally typical set. Okay? So that's the basic idea, right? And like tolerances, we're using the law of large numbers. So it's highly likely that the sequence, the output sequence will be in the typical set. And then given a fixed sequence, it's highly likely to land in one of these. And so you have these little epsilons, all of which you can make tend to 0 as the number of channel uses goes to infinity. Okay? That's the basic idea. We went quite a bit over time. Yes. So, all right. And then an important point is that what Shannon did, and we're not going to get into this, we'll get to it later. Shannon analyzed the expectation of the error probability over all possible random choices of code. Okay. So rather than analyzing the error probability of a particular code, he said, okay, let's look at the average of the error probability and show that that's small. Okay, so that's what he did using these kind of asymptotic arguments. And then what you can deduce is that, well, if the average is small, then there has to exist at least one code that has error probability equal to the average or smaller, right? The minimum of a set is always smaller than the average. Okay. And so this was the probabilistic argument. You know, he didn't give an explicit code, he just argued that there exists one. And it was an application of this probabilistic method that is very popular in mathematics and in physics as well. So that's the summary of the code in kind of a nutshell. Any discussion points? I should make one more point. We fixed the distribution to be this, but there's no reason to choose a particular one. You want to choose the one that has the maximal rate. So what you can do is maximize this mutual information expression with respect to all input distributions. And then that formula is the channel capacity formula. Right, so let's just write that down. The channel capacity P of y given x is equal to this. So this quantity right here was operationally defined, right? We said, blah, 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 there's exists a sequence of codes such that the error probability is tending to 0 as the number of channel uses increases, largest possible rate. It's like an operationally, physically defined quantity. That's this top. And then this right here is a purely mathematical expression, right? And so like, if I were to just give you this formula, you say, oh yeah, nice formula, right? What does it mean? Is it useful for anything? This is its meaning. So this capacity theorem gives a operational meaning to this mathematical formula. It singles it out as like a relevant thing. And what we'll do later is we'll say, okay, we'll make the channel quantum, and we'll seek out formulas like this for quantum information processing tasks. All right. Stop there. Stay safe, and presumably we'll see each other on Wednesday.